Okay, so in this class we're going to use chi-squared, and we're going to use this to make inferences with two-way tables. Okay, so there are two ways that this is used. One is to establish what is called homogeneity. Probably spelling that wrong. I'm going to leave it there. And the other one is to establish independence. Okay, these are really like two sides of the same coin, but they're slightly two different situations. Okay, so in the homogeneity thing, what we're trying to establish is that the sample is in the right proportion. Okay, so like in something like this, let's say that we were going to do something like gender versus political party, right? Then if we have a homogeneous reality, then the number of people that are, or the proportion of each gender that are in different political parties should all be the same. Okay? So this is one way of looking at it, is like, is everything aligned? Does the proportion of people, like the proportion of men that are Democrats equal the proportion of women that are Democrats? Does the proportion of men that are Republicans equal the women that are Republicans? The proportion of men that are independent equal the proportion of women that are independent? Right? Are these two, when I make the two-way table of gender versus political affiliation, do I get the appropriate response? Okay, that says like, it is aligned over both characteristics in a homogeneous way. Now, if that is the case, then I can also make a claim that gender and political affiliation are independent. Okay, because it would appear that gender is not influencing a political affiliation, and I don't know how it would happen that political affiliation would influence gender, but there's like that these two indicators are independent. So if the sample shows a certain level of homogeneity, then it also shows that the two characteristics are independent. This is like two ways of looking at the same thing from different sides. So let's take a look at a two-way table and try to understand like what this means and how it comes to be. Okay, so what we're looking at here is the question becomes does the same, so like one way is like what country the person is from in the sample, three countries that are all English speaking: Australia, the United Kingdom, and the United States. And then some opinions about how important is it to be an English speaker while living in those countries. And then it's labeled as very important, somewhat important, not very important, not at all important. And the question that we're going to ask first here is like, is this laid out in such a way that like it everything is nice and neat and proportional in every possible direction? Okay, so we're gonna get this like expected counts thing, okay? And the expected counts for each of these boxes, so like if I look at the Australia box, which should be the expected counts here, should be the total number of Australians. Okay, so the Australian and very important box is the one I'm looking at. The total number of Australians, which is 1,000, times the total who said very important, which is 2,569, over the total in the entire system, which is 3,463. Okay, so like off screen here, I'm gonna do a little bit of mathing, and I'm going to get 1,000 times 2569, and then I'm going to divide that result by 3463, and the expected value there should be 741.84-ish. Okay, so what I would expect to have in this box is 741.84 people. Now, the number that I have in this box is 690. So the boxes of interest in this problem is there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes that need to be dealt with. And for each of those boxes, we're going to get a chi-square contribution. So we're going to take the expected, the 741.84, minus the actual, 690, divided by the expected, 741.84, and the chi-squared contribution for that box, it'll be 741.84 minus 690 divided by 741.84. The chi-squared contribution of that box is going to be 0.0699-ish. Okay, and then what I'm going to do is I'm going to add up the chi-square contributions for all of these boxes. And as those contributions get bigger, the more I am moving away from homogeneity. So now the question is just like, what's the degrees of freedom on the chi-squared distribution that I'm using here? And the trick here is that you use rows minus 1 times columns minus 1. So in this, I have 1, 2, 3, 4 rows, so that's going to be 4 minus 1 is 3. And then I have 1, 2, 3 columns. You don't count the total columns, right? Just the ones that are the meat of the table here. Right, so 1, 2, 3 columns minus 1 is 2. So this is going to be lining up on a chi-squared distribution with 6 degrees of freedom. So then the question is like, if I use that chi-squared distribution with 6 degrees of freedom, and I add up all of these contributions, where does my number come to? What is my chi-squared number? And I'm going to get a p-value. Okay. Fortunately for me, the calculator can do all this work for me. And I really don't have to do a whole lot of heavy lifting. I have to know the number of rows. The number of rows is 4. I have to know the number of columns. The number of columns is 3. And I'm going to use the matrix functions on the calculator to help me here. So let me bring up my calculator. All right, so let me clear everything out of here. And I'm going to get a matrix. Okay, so I want that. I want to go second. And then I go down here to the X inverse button. The second that is cleaning up matrices. And I'm going to put my data in matrix 1, or matrix A. So I'm going to go over to edit matrix A. And I said earlier that this is a 4 by 3. It has 4 rows and 3 columns. So you see how it just made that matrix for me. And I'll put the data from the problem in there. So you can check this against the video if you want to. I got 690, 1177, 702, 250, 242, 221, 40, 28, 50, 20, 13, 30, right? So I have all the data in it, right? I don't use the total columns, just the ones that are in the meat of the matrix there, right? All right, so I'm going to go back to my main screen. I'm going to go second, quit, okay? Now if I go into second matrix, there's nothing in the B matrix right now. Going to B, it's completely empty, and that's okay. I'm allowed to leave it that way. I'll do that. Okay, so I'm going to go second, quit, back to the main screen. I'm going to stat. I'm going to go tests. Now I'm going to use a chi-squared test, not the goodness of fit test, just the regular chi-squared test. Observed. All my observed data is in A. I have nothing in B. I'm going to say that's going to be my expected matrix. Why can I put the blank matrix in there? Because the calculator is going to fill in B for me based on what is in A. That's kind of cool. It's going to come up with all those expected values. You don't have to calculate any of them. Does it? And then I'm going to go ahead and calculate. All right. So the chi-squared for this entire thing was 68.572. Okay, that's a pretty substantial chi-square. If I look at the p-value there, though, with 6 degrees of freedom, this thing is 8.02 times 10 to the negative 13, right? So my little p-value here is 6. What was it again? 8.02. 0.02 times 10 to the negative 13. Little tiny p-value. Okay, now remember, the H null here is basically everything is awesome, right? Like, all of these are in the correct proportion, everything is the way it should be. The reality is my p-value came out very small, so we're going to reject that H null, and we're going to say that this does not reflect homogeneity, okay? Something is not awesome in this table, all right? So let's kind of think about like what's going on there for a second. Okay, so I can get a little bit of an idea of where things have gone really badly. So what I can do here is I could take like the observed, so let's say second matrix A is the observed, and subtract the expecteds. So second matrix B is the expecteds. That's going to give me a matrix, okay? And you're going to see like where do I have negatives and positives and like considerable values, right? So as expected though, because the top numbers are larger than the bottom ones, but you could see where you're getting contributions, right? How far off are each of these numbers according to the reality? Now, getting down, like doing the whole matrix as once as a chi-squared thing is a little bit complicated because it gets into like matrix multiplication, which is beyond something that I want to do right now, but we'll kind of go there. Now, we'll go there later. Now, if you think about this, this also means that these things are not independent, okay? Because if they were independent, homogeneity would show up here, which means that people in these various countries are not independent about their opinion about how important speaking English is, right? So you have to dig deeper a little bit into the data to see who's, how that all lines up, but these two characteristics are definitely not independent. Let's look at a second test for independence here, okay? All right, so in our sample here, we had 1,200 participants, right? And they were, 760 of them were women and 440 of them were men, and they were asked about their perception about their weight. And do they believe that their weight is about right? Do they believe that they're overweight? Do they believe that they are underweight? And the question is does gender matter here, right? Does gender influence your perception about your weight? Now, so what we want to do here is we want to test for independence, right? So if we think about this, the H null here is going to be that there is no association, right? So the no association would be independent, right? The HA is that there's evidence of an association between these two things, right? So given the two-way table, can I do this? So remember, when I'm doing my chi-squared test, I just want the meat of the table, right? I want this part like right here in the inside. I don't want the totals, I just want that part of the inside. So I have a 3 rows by 2 column table, right? So let's get the calculator up here. All right, so second clear, let's just clear that off the screen. Okay, I'm gonna go into here and I want to edit. I'll use matrix A again. So now I'm gonna create a 3 rows and 2 columns table, right? And this was the number that was on that worksheet. It was 560, right? 295. 295, 163 versus 172, 37 versus 73. Okay, so now the question is like, does this give me evidence, right? So my null is that there is no association, right? So a high p-value is going to say they're independent. A low p-value is going to say that they are not independent and that there's some sort of association going on here. All right, so we go stat, tests, drive down to the chi-squared test, My observeds are in A. Doesn't matter where I put the expected, so I'm going to leave that in B. And I'm going to calculate. Again, got a really tiny p-value, 1.87 times 10 to the negative 13, right? Notice only 2 degrees of freedom, right? Because this was 3 by 2, so that's 2 times 1 is my degrees of freedom. So 1.87 times 10 to the negative 13. Really low p-value. So we're going to reject the null hypothesis, which says that there's no association, right? We're going to say that there is an association here, that your gender is actually not independent of your perception about your body image, at least according to the population that these 1,200 people came from, right? And again, you can kind of like take a peek under the hood and go look at B. See, now B also became a 3 by 2 matrix. These are the expected numbers that we were supposed to get there. You can compare those to the actual numbers, right? And get an idea. Remember, the left-hand column is female. The right-hand column is male. And it kind of gives you an idea of this. Okay? So there you go. This is like chi-squared tests with 2A tables for homogeneity and for independence. All right? So we'll work with this a little bit down the road here.